We now turn to the discussion section that Bindu will lead.
That is ruled out there, right? I believe. So production of high energy emission via interaction of cosmic rays with the ambient medium there. So probably that is ruled out, because for that we need probably larger emission regions, and we expect to see much more extended emission than sharp flares there. So that's ruled out, right? What are your thoughts on that?
I'm not sure I'm very familiar. I think, as I understand it, orphan flares have been sort of identified, and I do not know either way whether they satisfy Tony Reedhead's very sensible criteria as to whether they exist as a well-defined statistical phenomenon that has to be well-defined statistically as a phenomenon that has to be explained. But I think the explanations that were invoked were usually in terms of hadronic models, weren't they? Is that right? Those are the ones I know about, and I don't know any more about them now.
Is there any other question on the location of high energy emission? Of course, we don't have a clear understanding, so but if somebody wants to contribute or ask something.
Just one comment that we also need to start considering some non-conventional sources of seed photons, like some stray clouds. Actually, that's adding to Manel's point, which is what Leon Tavares et al. Have shown, that some stray BLR type of clouds could exist further out that can give you gamma ray emission at a much larger scale. So that is, again, non-conventional source of seed photons, but I think we need to keep our minds open to take those into account. And then again, my personal take is that instead of trying to really put gamma ray emission in one side or the other, we just need to go by spectral states of individual source, because that can change depending on when you're looking at it, and then the picture.
But that can also change if the emission location of emission region is at the same place, because that also depends.
Yeah, it can, which is what I'm saying. So we just need to go by state instead of trying to put it in one category or the other. That's my personal take.
Categorize according to Roger's criterion of how rapid the fluctuations are. I mean, are we all agreed here that if you've got very rapid fluctuations at TeV energies at timescales of an hour or so, or very short timescales of the from very close to black hole? Does anybody?
Very bright. It's a luminosity.
Yeah, luminosity
criteria.
Yeah,
so.
yeah.
If it varies by a factor of 10 or 50, then of course I agree with Roger that it has to be close to the black hole where we have.
Yeah. I have that's following the Roger's argument comment only. The problem is with when you say very, very, very short time variability, it demands a very small emission region. Am I right? So it's small emission region. Now the problem with the VHE is, so when I see a VHE photon from a blazar, that says the emission region is ahead of your BLR. Because if it is below the BLR photons can pair produce, and the TeV photon will be opaque to TeV. So if I see for FSRQ, if I see ever an VHE emission for an FSRQ, that says my emission region is ahead of BLR, but it may be possibly IR photon.
Well,
now the point is now we have to take along with the variable time scale also. This question was there. So you need to have a very compact emission region at a far distance from the central black hole, so means beyond the BLR region, so that Navalcheko and others, in fact even I also have one paper on it. So what we means, though it is very, or we can argue on it, one possible way how I can form a very compact emission region at a large scale in the jet is something like recollimation shock, which was never discussed here. So now as the ejecta comes out of the nozzle, you can always have a recollimation shock, which can actually compress back the jet. Now the argument is you can always say how much it can compress. Can it really compress to the variable time scale of 10 minutes? So these are all open questions. We really don't know.
Just a comment on that. The BLR or torus is not like a glass, like the TeV photons cannot escape. That also depend upon how rich the BLR region is. There is a probability that the high energy or TeV or GeV photons get absorbed there, but there is also a probability that they can escape from there. the object.
No, they cannot escape. It'd be opaque. If there is a BLR photon, if I keep a Lyman alpha photon in front of my...
So you have to keep, that's what I'm trying to say. It's not a glass which is, that the photons cannot pass. That also depend upon the opacity and how much the filling factor of the BLR region. So what I'm trying to say is that there is a possibility that they get observed, but there is also a possibility that they can escape. So this is what I'm trying to point out to you.
No.
So the BLR region, the broad line region or molecular torus or the thermal photons field which we have there, it's not like a glass that the high energy photons cannot escape. It's like a patchy structure, or probably it has a filling factor and it has an opacity.
Okay.
It's a photon field.
In the jet, it's been averaged.
So that has to be taken into account when we argue. I mean, there is a possibility that they get absorbed, but there is also a certain possibility that they can escape. So this is what.
Yeah, but the point is from the TV index, what you find out, the hard TV index when you are getting, even though a little bit of absorption is a big question.
So
Can I just
I
add
disagree.
here? I mean, I think this idea that you could get a generation of these very high energy photons at a range of distances is quite plausible. In fact, I mean, I think probably the extremely rapid time variations probably really do need to come somewhere close to the black hole. But I think we should keep in mind that what we need to get rapid variability in a more general sense is compact structures. Right? And we know that there are compact structures further out. There are people that love them and do modeling with them all the time in various types of shocks. So, it may well be that some of the emission is in intrinsically compact regions closer to the black hole, and some of it is actually further out, but in formations like shocks.
I disagree quite strongly about the BLR point. The BLR is patchy, but by the time you get to the jet, it's not like the broad line clouds are necessarily penetrating. So it becomes relatively isotropic, the distribution. And I mean, you can't, if the optical depth is something like 100 or to 10 to the gamma rays, they can't just escape by chance very light, most of them will be absorbed.
So I hear a lot shocks, acceleration, but let's step back. Shocks, acceleration happen without magnetic fields. Jets and AGN are powered by magnetic fields. It's hard to get rid of magnetic fields once you put them in. And you cannot really accelerate effectively electrons that would radiate if you have magnetization that's greater than 0.1, meaning you need to get rid of a lot of magnetic field, because initially the jets are really magnetically dominated, and then you can shock. But yeah, so this is what I vote for exactly. So now a way out is reconnection. So if you have a shock that doesn't accelerate, but if you have disordered field component, you can compress it and then trigger reconnection.
Well,
we found way out.
Thank you, Sasha. That was the next topic to discuss here. And we see few hands there.
I haven't finished. I also have another facet, another way. If you compress magnetic field, if toroidal field gets compressed, right, then it can become dominant, and then the jet can go unstable. And when it goes unstable, it can create current sheets that will reconnect. So you can have at least two ways in my mind how a shock actually can cause acceleration, but not in the conventional sense. You can either cause a reconnection of a disordered component, or you can cause the jet to go unstable. I think these are the two possibilities that are actually quite attractive.
Yeah.
I try. And I should apologize at this point to the observers here, because this further discussion may get rather theoretical, but do remember that you have the hospitality of a Center for Theoretical Science, and they may ask for their money back unless they hear some discussion of theory. I agree wholeheartedly with what Sasha just said. If you, in a conventional shock, if it's a magnetized region, you don't get a strong shock. And also, if there's another problem, if they're relativistic shocks, although there are seductive kinematic models, in practice it's terribly hard to make happen the sort of Fermi one-type mechanism that manifestly happens at non-relativistic shocks like supernova remnants. But I think in extreme cases, it is possible to create a relativistic shock that would be an efficient radiator in what we call a high sigma environment. That means one that's magnetically dominated. But this is a very different type of structure from the ones that are normally considered. And just to back up a little bit, the one way of thinking about this is that all of this strong electromagnetic field that we imagine exists close to the black hole, but not further out where the radio astronomers are looking, is like a sort of barrel of TNT or a white dwarf full of nuclear fuel, in that it's liable to detonate because you've got all this electromagnetic energy there. If you can convert it into high energy particles and then straight away into gamma rays, then you've done this job of changing electromagnetic energy into gamma rays, which is the challenge, I think, of this, the biggest challenge. It's not the only challenge by a long way. And you have to, and this is something that can happen obviously very fast over a large front, whereas the trouble with reconnections, it happens in a small volume, and you have to sort of wait for all the field lines to go through the reconnecting volume. And so that, whereas that can be, you know, that is probably the best way of making steady particle acceleration. It may not be the best way for making dramatic flares, which may be less of the emission. And the way I think this may work, although I can't claim that I know how to do it, but I think the way you may be able to make it work is to, if you can have which is probably almost certainly an oblique shock in an electromagnetic field, which would be formed by, you know, some sort of optical instability. Then you have this oblique shock, and then there's a sort of outflowing frame in which there's no electric field, but there is magnetic field. But in the frame of a stationary shock, the conditions are so abrupt that you create an electric field that is in the frame of the shock larger than the magnetic field in CGS units. And that's a Lorentz invariant. And that is the condition for dramatic runaway acceleration. And when an unsuspecting electron or positron finds itself in this environment, which you know, in one frame regards itself as a pure electric field, it then runs away like a linear accelerator until radiation reaction stops it. And that radiation reaction is what you're looking at with a gamma ray telescope. And if you can make a structure like that that has the sort of detonation going on with the dramatic, sort of essentially purely electric acceleration in a tiny shock volume, in a tiny shock surface, sorry, in a sort of shock surface, that's a very different type of structure from the ones that, you know, Sasha and I have thought about before. And that might be the way of having this sort of dramatic conversion of electromagnetic energy into gamma rays. Mm-hmm. And if I just bear with me for one moment and try one sort of supplementary idea which may make this a little bit easier to accommodate with the data, is to think about this sort of surface as being quite a wrinkled surface, and obviously moving and...
Which surface are you talking about, Roger?
This is a sort of shock surface or a detonation surface.
I see.
Detonation, really. And to associate with each point on that surface a direction of emission, because everything is relativistically beamed. There's a direction of emission. And if you then think about one observer looking at this surface as time changes, then you'll see certain spots on the surface when that direction is pointed towards you. And when those shocks come together, they create those points, come together, they create a caustic. And that caustic can make a bright spike of the sort that you see when you see twinkling of starlight and so on. And that can give you some gain. That can actually give you a sort of temporary sharp spike in emission. And the observations, just to come back to the observations now, what was interesting in the talk this morning was the analysis of whether or not you get FREDs, the fast rise exponential decays, or the DERFs, which is the opposite, or symmetric peaks. And I think generically in that sort of explanation, you'd expect equal numbers of FREDs and DERFs, although you probably could bias it in one way or another. And I think what I heard was you got more FREDs than DERFs, but they weren't symmetric for the faster flares. But that's a sort of observational thing. So sorry for taking so much time, but we paid our theory dues.